Hello, this is Paul Harmston. I am a sophomore studying physics at the University of Tennessee. This past summer, as part of the Student Mentoring and Research Training Program, I had the opportunity to join the Neutron Lifetime Research Group. My mentors were Dr. Nadia Foman and Dr. Jeff Green. This presentation covers a brief overview of research conducted to optimize the capture flux and beam profile of the next generation neutron lifetime experiment, BL3. The BL3 experiment intends to measure the neutron lifetime through proton decays. This experiment serves to improve upon previous measurements by reducing systematic effects and providing an increase in total events. Beam profile needs to be carefully characterized to guarantee it fits onto the detector and to maximize the capture flux. The methods by which this optimization is performed comes from having fine control over collimators located in the neutron transport beamline. We explored the parameter space relating the radii of the front and rear collimators as well as the collimator separation. This allows us to find a maxima of capture flux within the minimum size constraints of the beam profile on the detector. This work was performed using the neutron ray tracing software MC-STAS. Incremental parameters for radii and separation were fed into the simulation. Results were then filtered and graphed. About 20% of the rough parameter space was explored. The results illustrate expected trends in the flux data. Larger radii produced higher flux rates but had a shorter separation range over which the geometry had an acceptable profile size on the detector. The graph on the poster demonstrates this relationship for a constant front radii and varying rear radii and separation. This illustrates the relative capture flux in a family of radii parameters. When the full parameter space is systematically explored, a set of graphs can be compared. Additionally, a visualization of the neutron beam profile is shown. Most of the intensity of the beam is concentrated in the center of the spot as expected. The status of this experiment illustrates the importance of a known systematic effect, gravity. It implores the need to continue study into beam divergence and detector geometry. It was found that low-velocity neutrons fell outside the geometrical beam profile, and at large separations was equivalent to a few percent of the total intensity. This poses a problem that when a flux maxima is found, its beam profile will need to be re-verified. This effect does not impede the search for an optimal collimator geometry. To conclude, the data which was collected verified expected trends in the flux graphs. However, due to computational and technical limitations, the full collimator parameter space was not sufficiently explored. From the data which was collected, it shows that a local flux maxima can easily be located within a parameter space. The next step is to create a script which can procedurally run a mixed-task simulation with inputted parameters that scans over the entire allowed parameter region. An additional scripting system can then systematically analyze the set of data files produced from these simulations. This will allow for an efficient and scalable methodology to systematically locate a flux maxima from any set of geometric parameter spaces. Other researchers in the group can then use the optimal geometry in their own simulations.